Good day, everyone. So we are starting a new chapter today, chapter 13 of the Wetzel's Limnology textbook, edition number 4. And this chapter will focus on the inorganic carbon complex with Jonathan J. Cole with the Carey Institute of Ecosystem Studies in Millbrook, New York, and Yves T. Prairie with the Department of Biological Sciences at the University of Quebec in Montreal, Quebec. The occurrence of inorganic carbon in freshwater systems, carbon dioxide and its solution in water, the basic equations governing CO2 gas in water. The carbon dioxide content of the atmosphere varies with locality and with enrichment from industrial pollution. The global average is approximately 0.042% by volume as of 2021 and has been increasing recently at a rate of about 2 ppm per year, due largely to the emission of fossil fuels. Atmospheric CO2 in the pre-industrial age is estimated to be about 270 ppm, or 0.027%. As a gas, carbon dioxide is very soluble in water, some 200 times more so than oxygen, and obeys normal solubility laws within the conditions of temperature and pressure encountered in lakes. At equilibrium, the partial pressure of a dissolved gas is equal to the partial pressure of that gas in the overlying atmosphere. PCO2 water is equal to PCO2 atmosphere. Partial pressure is usually expressed as microatmosphere. So if the atmosphere has PCO2 of 400 microatmosphere, surface water at equilibrium with that atmosphere will also have a PCO2 of 400 microatmosphere. However, even when the water and atmospheric CO2 partial pressures are identical, their concentration per unit volume in the two media will be very different, as it depends on the solubility of the particular gas in water. The concentration of CO2 in the water is controlled by PCO2 water and a temperature-dependent solubility coefficient known as Henry's constant, Kh. So the concentration of CO2 is equal to Kh by PCO2 in water. Kh has units of micromoles per liter per microatmosphere, which is the same as moles per liter per atmosphere, and is about 0.04 at 25 degrees centigrade. CO2 behaves like most dissolved gases, that is, like oxygen. CO2, or carbon dioxide, is more soluble as the water gets colder. Another way to say this is that Kh increases with decreasing temperature. At an atmospheric partial pressure of 400 microatmosphere, for example 0.044%, the amount of CO2 dissolved in water at equilibrium with the atmosphere is about 30 micromoles per liter. At 0 degree, 19. At 15 degrees, 12. And at 30 degrees, and 12 degrees at 30, and 12 micromoles per liter at 30 degrees. So it's 30 micromoles at 0 degrees, 19 micromoles per liter at 15, and 12 micromoles per liter at 30. So you can see a decrease in the value of Kh with increasing temperature. As we will see, dissolved CO2 in the surface waters of lakes, rivers, and streams is often not at equilibrium with the atmosphere. The basic equations governing the distribution of the forms of dissolved inorganic carbon, DIC. As CO2 dissolves in water, the solution contains unhydrated CO2 at about the same concentration by volume, approximately 10 micromoles per liter, as in the atmosphere. CO2 air is equivalent to CO2 dissolved plus water. Dissolved CO2 hydrates by a slow reaction, a half-time of approximately 18 seconds at 25 degrees centigrade. CO2 plus water is equal to, or relates to, bicarbonic acid. This reaction predominates at a pH of less than 8, with the equilibrium concentration of carbonic acid only about 1/400 that of unhydrated CO2. Above a pH of 10, CO2 plus hydroxide is equal to bicarbonate is the dominant reaction. Thus, for most freshwaters, carbonic acid can be ignored compared to CO2. Carbonic acid is a fairly weak acid that dissociates rapidly relative to the hydration reaction. Carbonic acid equivalent to a proton plus bicarbonate. Bicarbonate plus a proton is equal to a proton plus carbonate itself. K1 is equal to proton by bicarbonate over CO2 aqueous. K1 in equation 13.7 is the equilibrium constant for the combined reactions of equations 13.4 and 13.5. The pK1 dissociation value of the first reaction, including both hydrated and unhydrated CO2, as the undissociated molecule is 6.43 at 15 degrees centigrade in dilute fresh water. A useful way to think about pK1 is that at pH 6.43, the concentration of CO2 and bicarbonate will be equal. Note that K1 is not constant, but varies with temperature, ionic strength, and some other ions, notably calcium. K2 is given in equation 13-11, and it is the equilibrium constant for equation 13-6. Look up the values of pK1 and pK2 for seawater, and you will see the difference, especially for pK2. To get the correct values in saline lake, you need to know the ionic strength and the ionic composition of the salts. So before we do that, let's look at figure 13-1. So relationship between pH and the relative proportion of inorganic carbon species of CO2 plus carbonic acid, bicarbonate and carbonate in solution. This diagram is common in limnology and water chemistry textbook, but often causes some confusions. First, it is actually the proportions of the forms of DAC that regulates the pH in natural waters, rather than vice versa, as the diagram might suggest. Second, the y-axis is the fraction, not the absolute amount. It is useful to remember that at pH 6.3, the amount of CO2 and bicarbonate are equal. Note that the value for pK1 and pK2 are appropriate for dilute fresh water. So this is y-axis is the fraction of total DAC, dissolved inorganic carbon pool, and then the x-axis is your pH. So you have three species here. You have CO2, bicarbonate, and carbonate. So at pH 6, we have CO2 that is equal to the concentration of bicarbonate, and that fraction is 0.5. Then at pH 10, or a little bit more than 10, we have the bicarbonate is equal to carbonate. So just what we saw in the text. Computer programs such as PHREECQ can do the complex calculation. The bicarbonate and carbonate ion also dissociate to establish an equilibrium. Bicarbonate plus water is equal to carbonic acid plus hydroxide. Carbonate plus water is equal to bicarbonate plus hydroxide. Carbonic acid is equal to water plus CO2. And K2 is equal to the ratio of protons to carbonate over bicarbonate. The pK2 of the second reaction is in dilute freshwater is 10.43 at 15 degrees C. So at pH 1043, the concentration of bicarbonate and carbonate will also be equal. So 1043 is right here. And then we have, as explained in the text, we have 6.3 right here. For example, in seawater, pK2 at 15 degrees C is about 9. This means that at the same concentration of calcium and carbonate will precipitate more in the sea than in freshwater. Range and origin of the DAC in freshwaters. Range of DAC concentration. DAC varies in natural freshwaters in a range of less than 20 micromoles per liter in dilute acidic streams and lakes to more than 5,000 micromoles per liter in hot water lakes, in hot water systems, greater than twice the level in seawater, and even higher in some saline lakes. At the pH of most freshwaters, greater than 6.8 but less than 10, bicarbonate is a dominant form of DAC. So we can see that. So most of our waters are going to be in this zone here. And what we see is that the dominant species is bicarbonate. Surface water concentration of carbon dioxide ranges from 6 to 100 micromoles in typical systems. CO2 is lowest during intense photosynthetic blooms and may be undetectable, as has been observed during some experimental fertilization of lakes. CO2 is highest when heterotrophic respiration is much higher than photosynthesis, or when external inputs in groundwater are high. By contrast, bicarbonate is typically between about 10 macromoles in mildly acidic waters and up to more than 5,000 macromoles per liter in typical hard waters, and even higher in some soda lakes. In hard water lakes, 90% or more of the DIC in hard water is as bicarbonate, which is often a major or one of the major anions in fresh water. The average concentration of bicarbonate in the world's major rivers is about 1,000 micromoles per liter, and values near this are common in many lakes, rivers, and streams, but depends on the geologic settings. Because pK2 is so high in freshwater above 10, carbonate can often but not always be effectively ignored for many calculations. For example, at pH 8 and 15 degrees C, the carbonate is only 0.3%, as abundant as bicarbonate. At pH 9, it is more significant, 3%, but still small in comparison. So if bicarbonate is 1,000 micromoles per liter, carbonate is only 3 micromoles per liter. At pH 8, and still only 30 micromoles per liter at pH 9. On the other hand, while carbonate is usually small in comparison to bicarbonate, it can still present a lot of carbon, especially if the total DIC is quite high. Origins of DIC. DIC enters aquatic ecosystems through several pathways. All three components, dissolved carbon dioxide, bicarbonate, and carbonate, can be imported via groundwater or from upstream systems, and all three can be exported in outflowing water. The carbon dioxide gas dissolved in groundwater is typically quite high due to the respiration of soil and plant roots. Concentration of CO2 near 1,000 micromoles are not uncommon in streams when they first exit the ground, and are even higher in natural groundwater. This is equivalent to PCO2 above 28,000 microatmosphere, or about 70 times greater than the atmosphere. CO2 additionally is captured and transformed into organic matter by photosynthesis and chemosynthesis. And organic matter is converted to carbon dioxide by both aerobic and anaerobic respiration. CO2 is also consumed in the weathering of carbonate or silicate rocks. Carbonate shells are the biogenic silica of diatom frustules. CO2 is generated by the precipitation of solid carbonate or shells and siliceous diatom frustules. Further, carbon dioxide exchanges with the atmosphere and surface waters can be either a source or sink for atmospheric CO2. If the PCO2 in the water is greater than that in the overlying atmosphere, the system acts as a source and vice versa. Bicarbonate is usually the largest component of DIC. Bicarbonate is a product of weathering of both carbonate, limestone and dolomite, rock, and silicates as well. The weathering is caused by CO2 in the air and in soil, water, due to the respiration of microbes and plants. For calcium carbonate, CaCO3, a generic weathering equation is CO2 plus water plus calcium carbonate is equal to calcium ion plus 2 bicarbonates. And similarly for silicate, 2 CO2 plus 3 waters plus calcium silicate is equal to calcium plus 2 bicarbonates plus salicylic acid. You will see many versions of these equations that may include magnesium, water, or other factors, but the overall idea is the same. Note that the atmosphere is the source of the CO2 in weathering, either directly, rock exposed to air, or more commonly, rock exposed to CO2 in salt water. That is, the CO2 in either case started out in the atmosphere. It was taken up during photosynthesis and was then respired either by the plants themselves or during the decomposition of organic matter. Globally, slightly more than half of the DIC transported by rivers to the ocean is derived from the weathering of carbonate rocks, and slightly less than half from silicate rocks. These values are obtained by tracking the cation and anion concentrations and discharges from the world's rivers. There are large regional differences in these values. For North America, about 80% of the DIC alkalinity discharge is attributable to carbonate rock dissolution, and only 20% to the weathering of silicate rock. Gaillard et al. Presented a table with 50 of the world's major rivers by discharge. The Seine, Rhone, and the St. Lawrence rivers are totally dominated by the carbonate weathering pathways, greater than 90%. The Orinoco, Zaire, and Irrawaddy rivers are dominated by the silicate pathway, greater than 80%, while the Amazon, the largest river by discharge in the world, is about 60% silicate dominated. At the local scale, both DIC and acid neutralizing capacity, ANC, concentration are usually much bigger in carbonate geology than in silicate geology. DIC and ANC are lowest in granitic schist and gneiss regions of North American and northern Scandinavia. Olivine and basalt, particularly in the climate of the humid tropics, weather more easily than does granite or gneiss in the colder climates at high latitude. So these tropical areas can have a moderately high DIC and ANC. Because river water discharge is also high in the humid tropics, these large rivers make the silicate pathways of ANC delivery to the ocean as large as it is. So before we move on, let's look at this table here, table 13-1. Process that either remove or add CO2 to the water column of the aquatic system. Atmospheric exchange. So we have remove CO2, process type, add CO2, comments. So remove CO2 is the first column. So the processes that remove CO2 is atmospheric exchange, photosynthesis, chemosynthesis, and carbonate dissolution. Process type. So physical process, photosynthesis is, of course, algae, macrophytes, periphyton. Chemosynthesis is related to oxidation of methane, sulfur, and ammonia, other electron acceptors. And carbonate dissolution is carbonate weathering. And so now let's look at processes that add CO2. Atmospheric exchange, aerobic respiration, groundwater inputs or surface water inputs, anoxygenic photosynthesis, and formation of calcite precipitation in water column or on plants, and macroalgae. Comments here. Direction depends on the partial pressure of CO2 gradient, so the direction in terms of the atmospheric exchange, because you can see that it either can act as a removal of CO2 or act as a way to add CO2 to the water column. All respiration including heterotroph and autotroph aerobic bacteria. And then chemosynthesis using sulfate, nitrate, iron as an electron acceptor, and then anoxygenic photosynthesis, purple or green sulfur bacteria, often in stratified lakes, and then formation of calcite, also shells of snails, bivalves, etc. Rare for pelagic organisms in freshwater, but common in benthos. So I think that's going to be it for today, and tomorrow we'll pick it up with this this carbonate iron. Okay, I think that's going to be about it for today, and tomorrow we'll pick it up with this subsection, the carbonate iron, and I'll see you tomorrow. Bye.